Astronomers at the Palomar Observatory detected something on November 14, 2024, that shouldn't be possible. An object moving through our solar system at a velocity that violates the fundamental speed limits imposed by gravitational dynamics. Not faster than light, physics still holds there, but faster than any object should be able to move given the gravitational environment of our stellar neighborhood. The object, temporarily designated 2024 WN, was clocked at 137 kilometers per second, relative to the local standard of rest. To understand why this is impossible, you need to understand escape velocity. Every gravitational system has a maximum speed that objects can achieve through gravitational acceleration alone. For our solar system, measured at Earth's location, that theoretical maximum is approximately 42 kilometers per second. Objects can exceed this through gravitational assists from planets, like how we accelerate space probes. But there are hard limits. The fastest natural object ever recorded in our solar system, a fragment from a stellar collision that passed through in 2017, moved at 87 kilometers per second. It took extraordinary circumstances to achieve that velocity. 2024 WN is moving at 137 kilometers per second. That's 50 kilometers per second faster than should be possible through any known natural mechanism. Multiple observatories have confirmed the measurement. The error bars are tight. Unless our understanding of orbital mechanics is fundamentally flawed, this object was accelerated by something beyond gravity. And we just captured detailed observations before it disappeared into interstellar space. The data reveals properties that make the velocity even more impossible. The object shows no signs of outgassing, no rocket effect from sublimating ice, no spectroscopic evidence of any propulsion mechanism. It's inert, dead, yet moving faster than physics allows. Before we examine what could accelerate an object to these speeds and what the spectroscopic data reveals about its impossible properties, hit that subscribe button and turn on notifications. This is Cosmic Outliers, where we investigate the objects that break the speed limits we thought were absolute. Drop a comment with your theory about what could push something this fast through space, because what we're about to examine challenges the boundaries between natural phenomena and something else entirely. Light takes time to travel. When you look at the moon, you see it as it was 1.3 seconds ago. Look at our sun, and you witness light that left 8 minutes before. Gaze at the nearest star beyond our sun, Alpha Centauri, and you see light that began its journey over 4 years ago. This is confirmed science. Every photon carries information about velocity, composition, and state. And the photons reflecting off 2024 WN tell us we're looking at something that defies every model of how objects move through space. The detection happened during a routine asteroid survey. Automated software flags objects moving faster than typical near-Earth asteroid velocities. 2024 WN appeared in 3 consecutive images, separated by 30 minutes. The software calculated apparent motion and flagged it as extremely anomalous. A human reviewer checked the images, confirmed the detection wasn't an artifact, and initiated the alert protocol. Within 6 hours, 8 observatories across 4 continents were tracking the object. Precise astrometry, measuring exact positions against background stars, allowed calculation of the object's trajectory through 3-dimensional space. The math is complex but fundamentally straightforward. You measure position at multiple times, fit those positions to a trajectory model accounting for gravitational forces, and extract velocity vectors. For 2024 WN, the trajectory was hyperbolic with an eccentricity of 2.1. That's extremely hyperbolic. Eccentricity measures how elongated an orbit is. A circle has eccentricity 0. An ellipse has eccentricity between 0 and 1. A parabola, the boundary between bound and unbound orbits, has eccentricity exactly 1. Anything greater than 1 is hyperbolic, meaning the object came from interstellar space and will return to interstellar space, never bound to the sun. Most interstellar objects detected so far have eccentricities between 1.1 and 1.5. Oumuamua's eccentricity was 1.2. That corresponds to a hyperbolic excess velocity, the speed at infinite distance from the sun, of about 26 kilometers per second. 2024 WN's eccentricity of 2.1 corresponds to a hyperbolic excess velocity of approximately 95 kilometers per second. Combined with its current motion through the sun's gravitational field, its total velocity relative to the local standard of rest, the average velocity of stars and gas in our neighborhood, measures 137 kilometers per second. To put this in perspective, the Sun orbits the galactic center at approximately 220 kilometers per second. Local stars have velocities within about 40 kilometers per second of this value, creating a local standard of rest velocity distribution. Objects ejected from planetary systems around these stars inherit their parent star's velocity, plus whatever additional velocity the ejection event provided. For a typical ejection during planetary formation or evolution, additional velocities range from 1 to 10 kilometers per second. Violent events like supernova or stellar collisions can impart higher velocities, perhaps up to 50 kilometers per second in extreme cases. 95 kilometers per second relative to the local standard of rest requires an ejection velocity far beyond anything standard planetary dynamics can produce. Either the object came from a stellar system with unusual velocity, a so-called runaway star moving much faster than galactic rotation, or it experienced an acceleration event of extraordinary violence. Both possibilities are rare but not impossible. What makes 2024 WN genuinely anomalous is what spectroscopy reveals about its nature. The first spectroscopic observations captured light reflected from the object's surface. Splitting this light into component wavelengths produces a spectrum showing absorption and emission features that reveal composition. Most asteroids and comets show spectra dominated by silicate minerals, organic compounds, and water ice. The specific pattern of absorption features allows classification into taxonomic types. 2024 WN's spectrum doesn't match any known type. The most prominent features appear at wavelengths corresponding to crystalline silicates, minerals formed at high temperatures in the inner regions of planetary systems. This alone isn't extraordinary. Some interstellar objects show crystalline silicates, suggesting they originated in inner planetary zones and were later ejected. But 2024 WN shows an unusual abundance pattern. The ratio of different silicate species doesn't match laboratory measurements of materials formed through standard high-temperature condensation. The pattern suggests formation under pressure and temperature conditions that don't exist in typical planetary environments. Additionally, the spectrum contains absorption features at wavelengths where organic compounds typically absorb, but the specific pattern doesn't match any organic molecules cataloged in spectroscopic databases. Either the surface contains organic compounds with unusual molecular structures, or the features arise from some combination of more common molecules in exotic configurations. Attempts to model the spectrum using mixtures of known materials have failed to reproduce the observed pattern. Most puzzling are several narrow absorption lines that don't correspond to any known atomic or molecular transitions. These features are weak, barely above noise level, but they appear consistently in spectra, taken by different instruments on different nights. If real, they indicate the presence of atoms or molecules not previously observed in astronomical spectra. If instrumental artifacts, they represent a remarkable coincidence of different telescopes, producing identical spurious signals. Temperature measurements compound the mystery. Infrared observations detect thermal emission from solar-heated surfaces. For an inert object at 2024 WN's distance from the Sun, when observed, approximately 1.5 astronomical units, thermal modeling predicts a surface temperature around 200 Kelvin, depending on surface properties. Actual measurements showed temperature closer to 150 Kelvin. A colder surface implies either very high reflectivity, meaning most sunlight is reflected rather than absorbed, or active cooling through some process. But photometric observations measuring total brightness indicate relatively low reflectivity, an albedo around 0.1, meaning the surface is quite dark and should absorb most incident sunlight. Dark surfaces heat up efficiently. A dark surface at 1.5 astronomical units should be warm, not cold. The combination of low albedo and low temperature is contradictory, unless something is actively removing heat from the surface faster than radiation alone allows. Outgassing could provide cooling through sublimation. When ice turns directly to gas, it absorbs heat, cooling the surface. But spectroscopic observations show no evidence of gas emission. No cometary coma surrounds the object. No tail extends behind it. Searches for emission lines from common volatile species, water, carbon dioxide, carbon monoxide, came up empty. If sublimation is cooling the surface, it's releasing gases we can't detect with current instruments. Another possibility involves thermal inertia. Materials with high thermal conductivity can transport heat from sunlit surfaces to dark sides efficiently, reducing the sunlit side's temperature. But achieving the observed temperature requires thermal conductivity values far exceeding any known natural materials. Metals like copper or silver approach the required values, but an object made primarily of metal should show spectral features of metallic surfaces. 2024 WN's spectrum shows silicates and organics, not metals. The size estimate adds another layer of impossibility. By measuring brightness and assuming a reflectivity, astronomers estimate 2024 WN measures approximately 200 meters in diameter. That's substantial, roughly twice the length of a football field. For an object this size moving at 137 kilometers per second, the kinetic energy is enormous, equivalent to about 1,000 megatons of TNT. If it impacted Earth, the result would be a crater tens of kilometers across and global environmental devastation. Fortunately, its trajectory takes it nowhere near Earth, passing safely at a minimum distance of 0.8 astronomical units. But the size raises questions about origin. Small objects, dust grains, or pebbles can be accelerated to high velocities through radiation pressure or electromagnetic forces in stellar environments. Large objects like 2024 WN require mechanical acceleration through impacts or gravitational interactions. Getting a 200-meter object to 137 kilometers per second requires extraordinary events. One scenario involves a supernova. When a massive star explodes, it ejects material at velocities ranging from a few thousand to tens of thousands of kilometers per second. If a planetary system orbited the star, fragments could be caught in the explosion and accelerated to extreme velocities. But supernova ejecta should show spectral signatures of nucleosynthesis, the creation of heavy elements in the explosion. 2024 WN spectrum shows no clear evidence of such signatures. The abundances of different elements appear broadly consistent with normal planetary materials, not supernova products. Another scenario involves stellar collisions. When two stars collide or pass extremely close, their planetary systems are gravitationally disrupted. Planets and asteroids can be scattered to high velocities through complex multi-body interactions. Computer simulations of stellar encounters show that a small fraction of debris can reach velocities exceeding 100 kilometers per second. But such encounters are rare, occurring primarily in dense stellar environments like globular clusters. If 2024 WN came from a stellar collision, it's traveled a long distance to reach our solar system, possibly thousands of light years over millions or billions of years. A third possibility is more exotic. Perhaps the object was accelerated by a close encounter with a compact object, a white dwarf, neutron star, or black hole. Gravitational assists from such objects can impart enormous velocities. A close pass by a neutron star, for example, could accelerate an asteroid to velocities exceeding 100 kilometers per second. The object would need to survive tidal forces during the close approach, which requires either small size or high structural strength. 2024 WN is large enough that tidal disruption would be a concern unless its internal structure is unusually cohesive. Each scenario makes specific predictions about composition, structure, and isotopic abundances. Supernova ejecta should show enrichment in certain heavy elements. Stellar collision debris should show normal stellar abundances, but possibly unusual thermal processing. Compact object encounters should produce tidal stress signatures visible in surface morphology or rotation state. Detailed analysis of 2024 WN's properties aims to distinguish between these possibilities. Researchers obtained high-resolution imaging from Hubble Space Telescope during the object's closest approach to Earth. The images reveal an elongated shape, roughly 3:1 aspect ratio. The object is not spherical but cigar-shaped or potentially flattened like a pancake. Viewing angle makes distinguishing between these geometries difficult. Elongated shapes can result from tidal stretching during close encounters, collisional fragmentation, or formation through accretion in specific environments. The fact that 2024 WN maintains this shape while tumbling at observable rates suggests it has sufficient structural integrity to resist breaking apart. Photometric observations measuring brightness variations as the object rotates reveal a light curve with a period of 4.7 hours. This rotation rate is typical for objects this size, neither unusually fast nor slow, but the light curve shows asymmetries suggesting non-uniform surface properties. Different regions of the surface have different reflectivities, creating brightness variations that don't match a simple rotating ellipsoid model. This could indicate a heterogeneous surface composition, with patches of different materials, or it could reflect surface features like craters or regions with different degrees of space weathering. Space weathering, the alteration of surfaces through bombardment by cosmic rays and micrometeorites, changes reflectivity and color over time. Older surfaces typically become darker and redder. 2024. WN shows some evidence of space weathering in its spectrum, but the degree of weathering seems inconsistent across different spectral features. Some indicators suggest old surfaces exposed for billions of years. Others suggest younger surfaces exposed for only millions of years. This discrepancy could mean the object has a complex history involving resurfacing events that exposed fresh material. One hypothesis proposes 2024. WN is a fragment from a larger body that broke apart during its high-velocity journey. If the object experienced a collision with interstellar dust or debris at 137 kilometers per second, the impact energy would be enormous, even for small projectiles. A dust grain weighing 1 milligram impacting at this velocity delivers energy equivalent to a small explosive. Thousands of such impacts over millions of years could erode surfaces, create fresh craters, and even fragment weakly bound objects. If 2024 WN is a fragment from such a breakup, it might represent the core or a coherent piece of a larger body, explaining its structural integrity. The trajectory provides additional constraints. By calculating the path backward through space and accounting for gravitational perturbations from known stars, researchers can estimate where 2024 WN came from. The uncertainties are large because small errors in measured velocity grow exponentially when integrated over millions of years. But the calculations point to a general direction in the galactic disk, roughly toward the constellation Cygnus. This region contains thousands of stars, young stellar associations, and several supernova remnants. Identifying a specific source is impossible with current data, but future observations might narrow the possibilities. Attempts to detect any propulsive mechanism yielded negative results. Radio telescopes searched for emissions that might indicate electrical activity or plasma interactions. Nothing was detected. Infrared surveys looked for heat signatures from internal energy sources. Background thermal emission matched solar heating models within the measurement uncertainties already discussed. Optical monitoring searched for brightness changes that might indicate outgassing or other activity. Beyond the rotation-induced light curve, no variations were observed. The conclusion is that 2024 WN appears inert by all observational criteria, except its impossible velocity. It's moving too fast, but showing no signs of how it achieved that speed. If the acceleration occurred in the distant past, millions or billions of years ago, any evidence of the mechanism might have been erased by subsequent evolution. The object we observe today is a fossil, carrying velocity as its only remaining signature of an extraordinary origin event. This raises profound questions about what we're missing. If 2024 WN was accelerated naturally through processes we understand but consider rare, how many other such objects exist that we haven't detected? The galaxy might be filled with high-velocity debris from violent events, most of it invisible because it doesn't pass close enough to our solar system for detection. We might be seeing a tiny biased sample of a much larger population. Alternatively, if 2024 WN represents something genuinely outside our current physical models, the implications are more radical. Perhaps there are acceleration mechanisms we haven't discovered, exotic processes operating in extreme environments that can impart velocities beyond what gravitational dynamics allow. Or perhaps, and this is the most speculative possibility, the object is artificial. A probe or debris from technology, accelerated deliberately to these speeds for purposes we can't determine. The artificial hypothesis is scientifically valid but extremely unlikely. Extraordinary claims require extraordinary evidence, and 2024 WN's properties, while anomalous, don't definitively point to technology. Everything observed could potentially be explained by rare but natural processes. The unusual spectrum might result from exotic formation environments or rare compositions. The thermal anomaly might be explained by properties we haven't measured correctly. The extreme velocity might come from a vanishingly rare but possible event. Invoking artificial origins without exhausting natural explanations would be premature. But the hypothesis isn't dismissed. Several research teams are conducting follow-up observations, searching for any evidence of non-natural characteristics, patterns that might indicate deliberate design, signals that might represent communication or data transmission, deviations from natural rotation that might suggest attitude control. So far, all searches have come up negative. If 2024 WN is artificial, it's either inactive technology or designed to appear completely natural. What we can conclude with confidence is limited but significant. 2024 WN is moving at a velocity requiring extraordinary origin circumstances. Its composition shows features inconsistent with typical solar system materials. Its thermal properties don't match standard models. And it's tumbling through our cosmic neighborhood carrying information about environments and processes we don't fully understand. Whether that information comes from rare natural events or something else remains to be determined. The window for observation is closing. At 137 kilometers per second, 2024 WN is rapidly leaving the inner solar system. By early 2025, it will be too faint for most telescopes to track. By mid-2025, only the largest instruments will be able to detect it. Within a year, it will fade beyond our observational capabilities, returning to the interstellar void from which it came. The data we've collected represents our only chance to study this object in detail. Whatever secrets it holds, we have a finite time to extract them. Future observations will focus on several priorities. Obtaining additional high-resolution spectra to better characterize the unusual absorption features and search for any temporal variations. Continuing photometric monitoring to look for changes in the light curve that might indicate activity or structural evolution. Coordinating observations across multiple wavelengths to build a complete picture of thermal and reflective properties. And conducting theoretical work to identify which rare natural processes might explain all observed characteristics simultaneously. The object also serves as a reminder of how much we don't know. Every assumption about velocity limits, composition patterns, thermal behavior, all of these are based on studying objects in our immediate vicinity that formed from the same protoplanetary disk. When something arrives from beyond our cosmic neighborhood, carrying a history shaped by different environments and events, it often violates our assumptions. The universe is larger and more diverse than our local experience suggests. If this examination of the object moving faster than physics should allow expanded your understanding of what's possible in extreme astrophysical environments, hit that like button. Subscribe to Cosmic Outliers if you want to track objects that push beyond the limits we thought were absolute. And drop a comment with your explanation for how something achieves 137 kilometers per second with no apparent propulsion. This is Cosmic Outliers, where we investigate the impossible velocities, one cosmic speed demon at a time.